All right, now let's look at problem 8. So problem 8 says Tom that he has a room low. He want to measure the depths of well. So first, what he did is he fold in from one into two, and then he fold three fold into three parts. All right, so this is the picture that we have. Okay. So now what we need to find, the problem asks what is the depth of the well. Okay, so what we can do is first let's find out the length of the rope. So let's say this is the rope, right? So I say, okay, so this is rope loop, which is x. So first it's fold into half, so this is x over 2. And then fold into three parts, so this is x over 3. Now, obviously, we see x over 2. So this is the well. All right. So what we have, so clearly, so the plus the 9, plus this 9, and plus this extra 2. So what we have is x over 2 is, which is the depth of the well. So this is the well depth. Let me write the other way. So this is the well depth plus 9, and then x over 3 is the well depth plus the 2, right? Plus this extra 2. Okay, so from here, so we can solve, obviously we have the difference x. So if you take the difference, your x over 2 minus x over 3, because the depth of the well is the same, though they just cancel the difference comes from those extra parts. Right, so this is 9 over 2, which is 7. From here is x over 6 is 7. So we get x equals to 42. Okay, so if x equals to 42, so the half of it, so this one will be 21, and 21 minus this extra 9, we derive this one is 12, right? So we get this one is 12. All right. So here the point is we introduce a variable and we set up an equation, right? So this can help us solve the problem very quickly. Okay. All right. Now let's look at problem number 9. So number 9 here says we have a triangle ABC and D is the middle point. So here the D is the middle point of AB and AE to EC. So this is divided into 1, 2 in terms of this portion. We know the area of this guy is 1, so we need to find the area of ABC, right? So total area of ABC. Now for this problem, there are two ways to do. So one way is we use pure area method. So we are going to use a method that is based purely on area. The second approach is we use similarity. Okay, so for this one, I'll just focus on the approach that only relies on areas. Okay, all right. So what we do is, let me remind you a basic fact. So this is very important, which is simple, it's very useful, but somehow I find a lot of students, they just don't know it. Okay, so it's the simple fact like this. Suppose I have two triangles. Let's put this. So this is triangle 1 and this is triangle 2. All right, so this is the length. Let's say this is A and this is the B. Okay, so now we have two triangles. They are adjacent. So their base is on the same line. Now the point is, these two, they share the same height. So the height is the same. So the height is the same. Now for this, we have the area. If you do area of 1 over the ratio, the area of 2, okay, so the ratio, because we know the area equals the height multiplied by the base, because they have the same height, right? So that means the ratio between these two is just, let me write out. So this is just A times the height, which is h, and then you multiply by 1/2. This is just the formula. And this is b times the h, and then you times 1/2. All right. And then we have some cancellation. 1/2 cancel, h cancel with h. So what you left is just equals to a over b. Right. So that's the point. If you have two triangles, if they share the same height, then the ratio between the areas is just the ratio between their bases. This is a very simple fact, but it's quite useful if you use it in a right and proper way. Okay, now let's do this. Okay, so in order to apply this basic fact, so what we do is, because here I already know that this is the middle point, right? So here's the middle point. So middle point, this is 1, 1. All right, so I add a helping line. Okay, let me add a helping line here. So I add a helping line. Okay, so then immediately, because so I get this is 1 and this ratio is 1, so I get this is 1. As I said, use the fact, right? So they share the same height, therefore the area, the ratio between their areas is the ratio between their bases. So this is 1. Okay, remember that. Now for this one, I don't know yet, so I put that this is x. So for this part, okay, again this is 1, 2, right? So this 2, so this, right? So I get this guy, it will be 2x, right? This guy will be 2x. Now for this, I put it to be y. All right. Now I'm going to set up equations. So in spirit, this one is kind of similar to the, I think to the one of the questions in last year's AMC8. Okay, all right. Then let's apply. So we say, let's apply this. So I look at this triangle, ABE, and then I have this triangle. Let me put it. So I have this triangle, BCE. So you see, again, so these are two triangles, they are adjacent. So they share the same height and the ratio between the base 1 over 2. Okay, so then I have the twice of, this is x plus 2 equals to, this is 2x plus y, so this is 2x plus y. Now, this one is the area of AEB, triangle AEB. So this is the area, so this is the area of triangle BEC, right? Okay, so that's what we have. So from here, if you do some algebra, you quickly figure out, let's see what we have. So this is 2x plus 4 equals 2x plus y. Okay, great. So we can just cancel 2x on both sides. I just get y, I get y equals to 4. Okay, so I derive y equals 4. All right. So now I can put a y to be 4. So I get a y equals to 4. So if y equals to 4, let's see what we can have. Let's look at this triangle, BDC. Okay, so BDC. So the area of this, will be 1 plus 4 equals to 5, right? And then, okay, look, this is 1, 1, right? So that means the other one, let me use this color. So then this guy, this one, so which is the triangle, which is ADC, right? So this triangle, so that this one is D, so this one is D. So angle ADC, this is also equals to 5 because the ratio is 1, 1. All right, so I get this is also 5, total 5, and this is 5, so it's 5 plus 5, which is 10, right? Which is 10. So here, the key point is we use this basic fact. Keep this in mind. This is very important. So if you have two triangles, if they're adjacent, right? So this is a typical scenario. So that means they share the same height. Then the ratio between the areas is the ratio between their bases. Now by this, so here what I do, an extra thing I did is I add helping line and divide it into triangles. Okay, so then I just put the variables, set up equations, and get what I want. Okay, so this is important. Now, you can look at chapter 6 of the textbook. So there's a section in chapter 6 that is specific for this technique. So for this basic effect, there's a section on chapter 6. It's about this fact and several applications. All right. Okay, now let's look at problem number 10. So this is problem number 10. So number 10 is about the pigeonhole principle. So here it says we have a bag, right? So let me put, so the bag has 9 variables. So I put the 9 variables, right? And then 8 variables. Okay, so variables. All right, okay. And then also have certain numbers of rubles, right? So we don't know how many of them. So this is some rubles. Okay, so Jack randomly picks some balls from the bag, and he says, if I pick, regardless how I do it, if I pick 9 balls out of the bag, then I can guarantee there are 4 balls of the same color. Okay, so this is one example of something called the pigeonhole principle. right? So you can look at the chapter 13. So chapter 13 of the textbook, that's about the Pigeonhole principle and other things. So there are several there. There are some interesting applications, examples of Pigeonhole principle. Now the basic Pigeon principle says, if let's say you have 4 rice cages, and then you have 5, say pigeons, right? 5 pigeons. You want to put 5 pigeons into 4 cages. Then the conclusion is there's at least 1 cage that has more than 1 pigeons, right? Okay, so that's the very simple Pigeonhole principle. All right. Okay, so this is just a variant of the Pigeonhole principle. Now, because you want to find a guarantee that at least 4 balls of the same color, right? Or 4 balls of the same color. All right. So what you think we can think of is the opposite, right? How you can make, let's say the opposite means how you can choose a ball so that you're not going to get 4 balls of the same color. So the words of, let's think of the opposite case, which is no 4 balls of the same color, right? So I want to design a way to select a specific way to select the balls so that there are no 4 balls of the same color. So then what you can do is, okay, so I say, well, I can get, say, 3 balls right here. I can get 3 balls of red, and then I have 3 balls of white, right? Okay, so now the point is, like, if you have more than 3 balls, if this one is more than 3, then what you have is 1 plus 3 plus 3, and then you need 1 more, right? 1 more. Then you get another 10, which means if there are no less, if there are say no less than 3 blue balls, then you need to pick 10 balls in order to guarantee that you can get 4 balls, right? All right, but here says he says he just needs 9 balls. So that means the number of blue balls is less than 3. Okay, so it's less than 3. Then it's very easy to see, okay, so I can get, I need to get 1 more. I need to get 1 more in order to get 9, right? So that means 9. So I get this one is okay. I get this is 2 balls, right? I get 2 balls. So the conclusion is there are exactly 2 blue balls, because if that's the case, the worst scenario you can do is 3 plus 3 plus 2, right? So that's 8. So it means if you draw 8 balls, you cannot guarantee that there are 4 balls of the same color. But if you get 1 more, right? If you get 1 more, then you'll get of the same, which is either red or white. Okay, so that means conclusion is 2. All right. All right. Now let's look at problem number 11. Rider flips the fair coin 5 times. Fair coins means it has equal chance to land on a head or tail. Now, what is the probability that there are no 2 consecutive heads? So let's recall how we calculate the probability, right? So this is called a discrete case, which means we have only finite many outcomes, right? Okay, so when you flip them, right? So how we calculate the probability? So this is the general formula. Say this is the total number of possible scenarios, and then you are only interested in the specific collections. You say, okay, what is the probability of that? Then the probability of A is just the number of elements in A divided by the number of elements in the total collection. So if I write in another way, so this is just the number of valid cases divided by the number of total cases, right? Total cases. Okay, so for this problem is we flip a fair coin 5 times, 1, 2, 3, 4, 5, right? Now what is the total number scenario? Because for each one we know it's head or tail, head or tail, head or tail, head or tail, head or tail. Then by multiplication principle, or by the way, so for counting problems, you can look at the chapter 3. So so in chapter 3, we collect all those basic concepts, formulas, and techniques for counting problem like this. All right, so for multiplication principle, because each have 2, so the total number of scenarios is 2 to the 5. So each have 2 scenarios, so you have to multiply them together instead of adding together. So this is something that for first learners, it's very easy to make a mistake. It's 2 to the 5. So the total scenario is 2 to the 5. So the total this is 2 to the 5. All right, so now you just need to figure out those good cases, right? Those are the number of valid cases. Valid cases means those arrangements where there are no 2 consecutive heads. Okay, All right, so that's what we need to do. Okay, so what do we do is we can do caseworks. Caseworks in terms of the number of heads you can have. Obviously, you cannot have 4 or more, because if you have 4 heads, then obviously, regardless how you do it, they are going to be 2 consecutive heads, right? So that the number in terms of the number of heads. So if the number of heads, the number of heads equals to say 3, then the only arrangement you can have is head, tail, and head. So then this is 1. So there's only 1 valid. So this I call valid cases, right? So these are valid cases. Okay. Now the second scenario is the number of head equals to 2. Now this is reduced, so that means the number of head is 3. So then you need to, okay, so you have 3 tails and 2 heads. You need to make arrangements so that 2 heads, they are not adjacent to each other. Okay, so for this, you can either do further, you can do another casework, or we have a general formula to handle this kind of situation, which is called insertion. So we have a technique, it's called insertion, to handle this kind of thing. Or sometimes people call like a bar and a ball insertion. So you can look at chapter 3. So it is there. So you can check the general statement. But anyway, so the point is that now you want to find, to accommodate 2 heads, right? But they cannot be next to each other. So what you do is you have, basically you have 4 positions that are separated by these 3 heads. So you want to accommodate these 2 heads into these 4 positions, right? You have to accommodate in these 4 positions. So what we do is just 4 choose 2, right? From 4 choose 2 positions. And with this formula, 4 times 3, 1/2, which is 6. All right. So for this scenario, there are 6, right? So there are 6 different scenarios. All right, so it's 1, 3, 6. Now the third, the number of heads equals to 1. All right, so then you can do whatever you like. So for this, we have 5 different scenarios. Okay, so there are last case, don't miss that. The last case is there's no head at all, right? So the last case is the number of head equals to 0. So for this, of course, there's only 1 scenario. So you have 1, 6, 5, 1, so you add them together, which is 13, So we get the number, of valid cases equals to 13. So this is, according to the formula, we put it right here. So we get this is 13 over 32, right? Over 32. So this is solved by the caseworks together with some technique or to put here, insertion bar and the ball, so that you don't have to do further casework. Okay, so now there another approach to handle this scenario, which is more specific for this situation, for this problem. Okay, so what you can do is, so this is, maybe I put this as the approach 1. Approach 1. Okay, so now I look at approach 2. Okay, so approach 2. So what is approach 2? Say now this time is you flip 5 times, right? So okay, so valid. Okay, if I flip 5 times, so this is the number of valid cases, right? If say this is rider, if rider flips 5 times, right? So we get is 13. So we get a 13. So now you ask, well, how about 6? What if I do 6? Right. So if I flip 6 times, 2, oops. Right. So if I flip 6 times, right? So I flip 6 times, then if you want to find for this case, what is the number of arrangements if there are no 2 consecutive heads, right? Now you can do is you can copy what I just did moments ago, right? You look at different cases and you apply different formula tricks from a counting problem. Another way you do is you say, okay, what I can go down from 6 to 8, right? So 6 to 5. Okay, so I look at 2 cases. The first case is the last one is head. If the last guy is head, and then the second case is the last one is tail, right? So the last one is tail. Now, if the last one is head, then the 5th one, it has to be tail because we don't want consecutive heads, right? So this one has to be tail. So then all you need to do is to arrange the zero, like the first four, you want to make sure, okay, so there are no two consecutive heads. So that means this guy is A4. A4 means if you flip 4 times, what is the number of arrangements that there are no two consecutive heads, right? All right. And the other, okay, so now how about this guy? This guy, if the last one is tail, then for the previous 5, you can do whatever you like, as well as you can make sure there are no two consecutive heads. So this is just A5. It's the same scenario as you flip 5 times. Okay, so then, so this is A6, right? Okay, so then I get a recursive relation. A6 equals A5 plus A4. And this is like a Fibonacci sequence, right? So similarly, you have got A7 equals to A6 plus A5. And you can also A5 equals to A4 plus A3 and such. So this provides Fibonacci. So it has the same pattern as the Fibonacci sequence, right? Okay, so Fibonacci sequence. Well, except that the first 2 elements are not the same, but the pattern is it's the same. The next one equals to the previous one plus the one before previous one added together, okay? All right, so this is, of course, you can move forward to get all the numbers. All right, so here you have the first one is you just go with the usual approach to find. Okay, anyway, so that's what we have. So here the main point is number one thing you should know is how you calculate the probability. If you have discrete case, you have only finite many scenarios. So what you do is basically it's fraction. Probability is fraction. It is the fraction of the whole thing that is what you want. So the number of what you want divided by the number of total cases. Okay? All right. Okay, now let's look at the number problem 12. So this is a problem about the coordinate geometry. So coordinate geometry is we have a coordinate plane, and each point is represented by a coordinate right here, right? So this is K5. Okay, so this is it's K5. So this is K5. So P is so this guy is 3, and Q is 4, 0. So this is 4, right? Okay. So now you also see each lines. They are also represented by equations. Right. So the coordinate geometry is basically we transfer geometric relation into algebraic relations. Okay. Now let's look at this. K. So K is the x coordinate. So this, which means this one is K. And this is 5, so this is 5, right? So we get this is 2, okay, so this is 3, and this is 4. All right, so here it says the area of this one is 8. So the area of this guy is 8. All right, so from here we are able to establish an equation of K. Okay, so how we calculate the area of this? So the area of this is the area of the trapezoid, right? So it's the trapezoid. It's the trapezoid, the whole thing. So which is the trapezoid, and minus 2 triangles, right? 2 right triangles. Okay. So we can calculate. So what is the area of this triangle? So the area of this is so this is 6, right? This is 6. The area of this one will be just K. So this is the area is K. All right. So what is the area? Okay. So let me put it here. So the area of maybe let me put an R, then put this is S. So area of the trapezoid, so which is RSOQ. So this one equals to the top one plus the bottom, and then multiply by the height. So the height is 5 and divide by 2, right? Okay, and then you minus, then you subtract. So the area of these 2 right triangle, one is 6, one is K, another one is 6. So I get equation, I get this K plus 4 times 5 minus K and minus 6, right? So minus 6 equals to 8. Right? So it's the trapezoid minus one right triangle on the top and one triangle on this corner, and you put together. And from here, then you just solve the equation. So you solve the equation, you get a K is 8/3. All right. Okay. All right, so now let's look at problem number 13. So here, so problem number 13 is we have two semicircles, a big one, a small one. What we're going to find is the area of the yellow region. Now, of course, at least for now, we cannot do this directly because the yellow region is a curved one, right? Curved one, we have to, in order to calculate its area directly, we need to use calculus, which we haven't learned so far. Right, so what we should do is we do a cut and paste, right? Basically, it's kind of cut and paste. So the point is, so here what do we see? So this is 2 and this is 2, right? So if, okay, so this is the middle point and it's an isosceles triangle. So if you choose the middle point, it's perpendicular. So isosceles triangle, the middle point, the middle line, the median is the same as the height, right? Okay. All right, so then here we have this 2. Now, as we calculated before, this is isosceles. So this is 45, this is 45. So let's recall. So if I have isosceles right triangle, if the hypotenuse is 2, so we know this guy is square 2 and this is square 2. So this is what we did before, remember? Okay. So, well, so then I have this is square 2, I have the square 2. Okay. Then you see the area of this quarter circle. So the area of this quarter circle equals to 1/4 times the total area of the full circle, which is pi times 4. That's pi. Now let's see what's the area. So let's look at the area of this semicircle. So let's look at the area of this semicircle. Okay. So area of this small semicircle equals to 1/2 times pi times the square of its radius, which is square root 2. So square root 2 is its radius, square root 2, so it's right here. So square root 2 squared. Again, you get is pi. So that means they have the same area. And meanwhile, you see they share. They share this sector, right? So this sector. Okay. So that implies. So what we have is okay. So we implies this part equals to that equals. So equals to this right triangle. They are the same. They are the same, right? So we get they are the same. So this is 2 and this is 2. Okay, so then we just get the area of this equals to 2. Right? Okay, so the point is, so let me repeat. So by the total calculations, we use a product theory and we figure out the radius of the small semicircle, which is the square root 2. So this is square root 2. All right, so we found the area of the quarter circle and the area of the semicircle, they are the same. And we find they share this green part, right? So they share the green part. Okay, so that means if the area is the same, if they share a common part, so if you get rid of the common part, the other two parts shall be the same, right? So we get this curved part is the same as this purple. That's a purple, so it's a purple right triangle. So we check at this too. Okay. All right. So like if you see a problem like in AMC10 or AMC8, if you need to calculate the area of some curved region, almost certain that you need this kind of cut and paste. You just put things together into some nice regions because we don't know how to we don't know calculus, right? Let's say we don't know calculus, then we cannot calculate the areas directly. All right. Okay, so number 14. So number 14 says Austin has an interesting 2-digit number. He found like if you reverse the unit digit and the tens digit, okay, and if you add them together, get a perfect square. So let me write down the assumptions. Okay. So Austin has a 2-digit number AB, and then he reversed the two to get this BA, right? And then he add them together, so it's AB plus BA, and together equals to square, right? So it's a perfect square. It's a perfect square. So n equals to a perfect square means it's square of another number. So let's say it's n squared. Okay, it's perfect square. All right, so you need to figure out basically what this guy is. Okay. Now, so here we use an algebra. Let's write this one out. So this is just 10a plus b, right? So this is how we express the 2-digit, and this is 10 times b plus a. Okay, so we combine like terms. Okay, so this one equals to 11a plus 11b equals to sum squared. And this is 11 times a plus b equals to m squared. Okay, so now you see, on the left-hand side, which is divisible by 11, that means, and 11 is a prime number. So that means the right-hand side also has to be divisible by 11. So that means n is divisible by 11 because you cannot split 11. All right, so then I get n is divisible by 11. Well, but meanwhile, you see the a plus 1, a plus b, because they are both digits, so the at most is 18. So now if you combine those things together, right, it's mostly 18. So if you combine those things together, you get the m square has to be just 11 square, right? It cannot go bigger, otherwise it will go beyond. All right, so then if you put those things together, you will get this, that is the only choice you can have, right? So then what you have, you get this is the 121, and then you add number together, so you get n equals 121, and so it's 1 plus 2 plus 1, which equals to 4. All right, so here the main point is we need to use some algebra, right? So if you have number, you reverse it. So add it together, then you can combine like terms and you can pull the 11 out. So it's a multiple of 11. Okay, so 11 is a prime number. So if it's a perfect square, it has to be divisible, the number has to be divisible by 11. And combine all those information together, we figure out the n has to be 121, so that's 4. Okay.